Okay, so now we've gotten to the point where we're going to talk about lemniscates. So lemniscates are pretty famous looking curves. You might recognize certainly this one looks exactly like the infinity sign. It is in fact what the infinity sign is based on. And so they have a strange equation. They are r squared is equal to a squared sine of 2 theta, or r squared equals a squared cosine of 2 theta. So we don't really do much with them, but they're famous and they're kind of interesting to look at. So I definitely wanted you to be familiar with them. There are two fun facts that are in the notes. The first one is that the infinity sign is actually a lemniscate, and it was once a question to an answer on Jeopardy, because if you know how Jeopardy works, they give you the answer and you have to give them the question. And the question was, what is the infinity sign? No, it was probably like, what is a lemniscate? And then the answer that you were provided with was like, this curve is the infinity sign or something. And then the other weird thing is that the area contained within a lemniscate is actually just a squared, which is pretty crazy. So for this first example that we're going to do, where r squared equals 36 sine of 2 theta, the area contained within the lemniscate is actually 36. 36, just the number 36. How crazy is that? All right, so r squared equals 36 sine of 2 theta seems like it's going to be hard to deal with, but what I'm going to do instead is I'm going to take square root and see if that's going to help me. So I'm going to say r is equal to either plus or minus 6 square root sine of 2 theta. Okay, so there's kind of a lot going on there. That square root is going to cause trouble for anywhere the graph of sine of 2 theta is negative. So those just won't be in the domain. So not really a big deal. And then there's plus or minus, so that's weird. So what I'm going to do, I'll use two different colors and see what's happening, right? So, all right, so this will be 6 and then negative 6. So I'm going to dot in. It's like when we're doing secant, cosecant. I'm going to dot in a guide function and then use it to get the actual graph, I guess. It's not going to be perfect, but I know that the square root, so the values are always, the value of sine is always between -1 and 1. So the square root of that is also, well, you can't take the square root of anything negative. So basically you're stuck with 0 to 1. So that's okay because I'm still just scaling it by 6. So I'm going to basically be graphing the sine of 2 theta, only caring about it where it's positive. And I know that it should actually look a little different from how it's going to end up, but this will give me enough for an idea of what to do. So it's 2 theta. So the period is pi. And then there, it says pi over 2. All right, so it's sine here, here, here. It's going to go negative here, so that's not going to be there, but we'll see. And then maybe I should go past this. I'll go with 3 pi over 2. And then there. Okay, so let me sketch this, this, and then it's going to disappear because it'll be negative. And then it's going to come back into existence. I should have put a point to aim for, like that. Okay, so how can this help me graph? Well, keep in mind there's also simultaneously this graph, which is just the negative. And like dotted, whatever, and then there. So you can make a case that to get the entire graph that we're going to want, all you really need is 0 to pi over 2. Because between 0 and pi over 2, you're tracing both positive and negative r's. Because this isn't really a function, like it's r squared, it's kind of implicit. So let's see. So I'm going to take theta equals 0 and theta equals pi over 2. I'm going to dot those in as tangent lines. So 0 and then pi over 2. And let's just see how the curve is sketched, right? when I get to pi over 4, I need to be out at 6. So pi over 4, I'm going to be out at 6. Count by ones. And I'm just going to swing out, right? So from 0 to pi over 4, we increase. From pi over 4 to pi over 2, it's going to decrease. Okay, and then it just kind of disappears between pi over 2 and pi, and then it's going to show up again when we get to pi. So pi, we're at 0 again. When we get to 5 pi over 4, we're going to be at positive 6 again. So it's like it was waiting, just doing nothing. And then, so that's from pi to 5 pi over 4. We're going to go from 0 out to, so it's kind of weird. You're here. This one almost does make a sharp turn, but it doesn't make a sharp turn because it just disappears on that time interval from pi over 2 to pi. And then it's going to go back in like this. So if I were to label this up, I think this is a useful thing to do, like we did with rose curves. This was 1, this was 2, this is 3, and this is 4. And that's kind of weird because that doesn't necessarily feel right while you're doing it. So we got 1, 2, 3, 4. You could also make a case that between 0 and pi over 2, you're just graphing parts 3 and 4, but you would be graphing them in brown, and then you would just be done with the entire graph. But anyway, this is our first lemniscate. Definitely not the more famous of the two. I'd say the more famous by far is a cosine lemniscate, because that's actually the infinity sign that we're used to. I'm going to do the same thing, though. So we'll be at, because I'm doing the square root 2 and negative 2, right? So r is plus or minus 2 square root cosine of 2 theta. Okay, so I know that I'm going to go pi, and then let me just go to 2 pi just in case. There, there, there. So it's cosine. I'm going to do the positive cosine one. Here to here, then it'll disappear, and it'll show up here, here, and then you need to go 1 past to get that. All right, let me see here. So there, and then it'll disappear because we're negative, and it's back to there. So I think a good idea here is to back up a little bit and do this. So this is pi, so this is pi over 2. That'll be pi over 4. So this will be negative pi over 4. So I'm going to use pi over 4 and negative pi over 4 as my tangent lines, and then I will graph it. So pi over 4, and negative pi over 4 is coterminal to 7 pi over 4. And 3 pi over 4 is kind of the extension of that. Okay, so when theta equals 0, I need to be out at 2, and by the time I get to pi over 4, I need to be at 0. But I'm going to think of it a little differently. I'm going to count by, I'm just going to put a tick mark here that say that that's 2. But I should probably write 2 instead of 4. 2. Okay, so what I'm actually thinking is when theta equals negative pi over 4, I'm at 0. Then by the time I get to 0, I'll be out at 2. And then when I get back to 0, it'll be pi over 4. So what that's going to look like graphically is this. So I'm first tracing kind of in the, let me switch up my color. Okay, so I'm going to start here. So I'm going to go like this, and then like this. And then you pause, right? And you do nothing between pi over 4 and 3 pi over 4. Then at 3 pi over 4, it's like you come back to life, and suddenly you're going to graph again. And by the time you get to pi, you got to be out at 2. Be out there. So you're going to go like this, and then like this. So it's weird the way that I've graphed this. It's 1, 2, and then these feel like they have sharp turns. I imagine that there's like an imaginary part or something that's happening when you go negative. It's in like some other complex plane or whatever. I mean, I'm saying I imagine that because I'm actually just imagining that. I don't actually know that. But there must be something going on like that. So we get that. And that is our infinity sign. So our infinity sign is a cosine leminiscate. The sine one, I don't know. Sometimes I use it. It looks kind of like the propellers of an airplane to me. And so I'll use it that way sometimes if I'm doing like artsy little things or whatever. Okay, so I'm going to end this here and come back with more.